Welcome to Calculus. I'm going to work another problem from 3.6. This is going to be very similar to number 10, the one we did in class on Friday, and this is number 11. So this is again section 3.6, number 11. This is going to be long. This will take a while. I don't know how long, but take a few screens. So hope this is helpful. Number 11. We're going to sketch y equals 2x over x squared minus 1. So there's really, I guess, three parts to the analysis of these functions before we graph them, so we have to do each one thoroughly. I'll probably take a screen to do each one. The first part is the pre-calculus part, so no calculus required. And in that case, you probably want to factor things as much as possible. Do any kind of simplifying that you can. And the denominator is factorable, but there's no simplification that will occur. But that does help us quickly determine the domain. You can see that x cannot be 1 or negative 1. And I could write all reals except 1 or negative 1, I suppose I should say. All reals with that disclaimer, such that x is not negative 1 or negative 1. And that means it's a vertical asymptote there. And this will actually help us when we graph it. X equals negative 1, x equals 1. Those are vertical asymptotes. Horizontal asymptote, you do not need to do the technique we learned in section 3.5. And this pre-calculus analysis, you can use what we learned looking at this form right here. And you see that the denominator has a greater degree, so that means the horizontal asymptote is at y equals 0. Lastly, we want to find the intercepts. If x is 0, what has y become? Well, it becomes 0, so the x-intercept is 0, and you know what that means. When the x-intercept, oh wait, that's the y-intercept, but anyway, when the x-intercept is 0, the y-intercept is 0, so they're both 0. And again, in review, how do we get that? Firstly, I'll show you how you get the y-intercept. The y-intercept is where you plug in 0 for x. And that, of course, is 0 over negative 1, which is 0. So that means when x is 0, y turns out to be 0. So that is our y-intercept. But if 0, 0 is a y-intercept, it's going to be an x-intercept. Is it the only x-intercept? Well, recall the way we find our x-intercepts, we set the numerator equal to 0, and that's all we're going to get. So we will be ready to put that on the graph. So we might want to note these things when we go to graph, especially the key ones are the vertical asymptote, that will go on the graph, the horizontal asymptote will go on the graph, and then plotting that point. Okay, let's go to the next screen and do the derivative. Okay, so the derivative of, I'll write this down again, I'm going to put it in the original form because it will be easier than the factored form. So the derivative, we're going to need quotient rule. Just going to go ahead and copy down the denominator, copy the denominator, write the numerator, minus write the numerator, derivative of the denominator. Anything in common? 2. I don't think 2 is worth pulling out. I think I'm going to leave it there. And we'll have x squared minus 1. Maybe we'll pull that later. We'll see. Why not to pull it out? Let's do it. So we pull out 2. We have x squared minus 1. That little thing there. Oh, sorry. My eraser is too big. X squared minus 1. And then we pull a 2 out of here, and we have minus 2x squared. We have a common denominator left over. We will always have a common denominator left over. Forgot that 2 there. Well, that didn't throw you off. There does need to be a square in the denominator. I think that got eliminated when I did my big eraser. So we have 2 times negative x squared minus 1 all over x squared minus 1 quantity squared. No, nothing cancels. The numerator thing in the parentheses has two negatives, the denominator has 1. They don't cancel. I'm going to pull that negative out, however. So it'll be negative 2 times x squared plus 1 all over x squared minus 1 quantity squared. Okay, the question we have to ask ourselves is, where does this equal 0 and where does it not exist? Well, it can equal 0 because the numerator can't equal 0. So I may make a note here and say there are no zeros. But it can equal 0 because I could factor this to x plus 1, x minus 1, all squared. The squared doesn't really matter. That tells me x can't really be 1 or negative 1. But you know what? We got that from the pre-calculus analysis. But we do need to pay attention to that. Okay, now we got our critical numbers. These are critical numbers. You can read that. So I do my little test. I test at negative 1. I test at 1. So again, the idea is a critical number is a place the slope could change from positive to negative or negative to positive. You could have an asymptote there, which we do, and we don't really know what's going to happen. So we better check to see if there's a change in slope. So I'm going to check left of negative 1, negative 2, right of negative 1, 0, and right of 1, 2. And see what the slope is in those regions. When you put negative 2 into the derivative function, and that's in here, let's see, the denominator is squared, all squared, so it's going to be positive no matter what. The numerator, you're going to square your x first. It's going to be positive no matter what. So this is positive no matter what. This is positive no matter what. You add 1, it's still positive. You multiply by 2, they're all negative. Negative, negative, negative. So what does that mean? That means it is always decreasing, at least over its domain. So you could write that. Okay? And it also means there are no extrema. We're not too disappointed, are we? Don't have to do really anything else, but the graphing might be kind of tough because we got nothing from here except I guess it's always decreasing. So on to the second derivative test. Okay, second derivative. Our first derivative in its most simplified form, and this is going to get a little bit long, so I'm going to try to squeeze it in here, was this. Ignore that stray mark under the square up top. Okay, so if we take the derivative, we write the denominator, which is x squared minus 1 all squared, times the derivative of the numerator, which would be that negative 2 is hanging around. And the derivative of that's going to just be 2x, right? Then we're going to do minus the numerator times the derivative of the denominator, which will be, what? You help me, 2. 2 times Elmo, as we say. This goes around, and then this becomes a 1. So there's a 1 exponent at the end of this line. I'm not going to write it. But then chain rule says, don't forget 2x. All over what we had previously squared, which is going to now be to the 4th power. Let me check myself. Everything looks good. Anything we can pull out of this? Hopefully there will be. Of course, x squared minus 1. Let's see, we got 2's. You know, this negative right here, I'm actually happy with. I'm going to let him make that a plus. So I'm not going to pull out negative 2, but I could pull out 4x, right? So I'm going to pull out this, put a little star over it, and this, that's 4x. And I will pull out this and this. The remaining thing is that negative. So I do have, oh, I forgot to remove 4x. Let's just start over. So I'm going to pull out 4x, x squared minus 1. So what is left? An x squared minus 1 and a negative 1, right? That negative comes from here. And of course, I only pulled out a single x squared minus 1, so there's one of those left. Then we have a plus. This 2 is still with us. This x squared plus 1 is with us. And that's it, because these guys all got taken. 4x x squared minus 1. Look good? Let me check. Okay. Don't forget your denominator. That's always sad. And you know what? This has happened before, but this is going to cancel with this. So you guys see that? Let me change the color. This is going to cancel with that. So that becomes a third power, and this is gone. That's nice. See what's left. We have 4x. We have negative x squared plus 1. We have 2x squared plus 2. We are going to have like terms. We always have like terms after we factor out. No, I'm not surprised. So finally we have 4x, x squared plus 3 over x minus 1 quantity cubed. Done it. Okay, any zeros? Can you make the numerator 0? You can. You can indeed. If x is 0, it's 0 because of that. This cannot be 0 still. So there's no more zeros. And the denominator, 1. Ooh, you know what? I missed the square, didn't I? Hopefully you didn't get confused. That should be squared. Right there. So because of that, again, x can't be 1 or negative 1. That continues. I'm going to try to squeeze this in here. You, of course, will have more space in your paper, and this will work much better. I need to check all of those. So I'm going to have 4 intervals to check. The first one, f at f double prime, at something less than negative 1. How about negative 2? Then we'll check negative 1/2. Then we'll check positive 1/2. Then we'll check 2. Okay, I don't really love the idea of putting in fractions, but I think we can figure this out. Let's take a look. If you put, no matter what you put into here, it's going to be positive. You square it, you add 3. This term is going to expose the sign, so if you put in a negative, it's going to be negative. If you put in a positive, it's going to be positive. So the numerator will reflect overall the sign inputted. Let's look at the denominator. It's cubed. That's not going to help us. So x squared minus 1 means if it's bigger than 1, it'll be positive. If it's less than 1, it'll be negative. So this one is going to be negative up top, and then down below it's going to be positive. So this one is negative. This one will be negative up top. This one will be positive up top. This one will be positive up top, because the top uses the sign that's inputted because of the 4x term. Down below, if you have a number less than 1, when you square it and subtract 1, it's going to be negative. When you cube it, it's still negative. So this is negative over negative, or positive. This is positive over a negative, which is negative, because in both this case and this case, if you square it, subtract 1, it's still negative. Finally, this one is going to be positive over positive, and that's positive. So we have a nice NP combo. So let's change colors yet again, just because we can. This is going to be concave down from negative infinity to -1, and then it stops. But then from, what was that? Then from 0 to 1, it's going to be concave down again. Concave up is going to occur from -1 to 0, in union with 1 to infinity. And that means we have a single inflection point. Bear me, I'm going to put this at the very top. So our inflection point is going to occur, well, it looks like we could have three inflection points, because we have 3 places where the concavity changes, -1, 0, and 1. But inflection points are points, they're on the graph. And -1 and 1 aren't in the domain, so we don't have to worry about it. Our only inflection point is at 0. And if we plug in 0 in the original, what do we get? Well, 0. That's our x-intercept and our y-intercept. No shocker there. Our inflection point is that x-intercept and y-intercept, 0, 0. Now we're ready to graph this. Okay, graphing. So assume you have all your key information in front of you. There is going to be a vertical asymptote at x equals 1, vertical asymptote, x equals -1, horizontal asymptote, y equals 0. And if you have 2 vertical asymptotes, your graph can cross the x-axis, and it can cross the horizontal asymptote, and it's going to happen here. That's our only point. 1 point. Great. But we can do this. This one is always decreasing. So how can you always be decreasing? Let's deal with this over here. Left of this left horizontal asymptote. If you're always decreasing, you can't be up here. How could you be up here and have this horizontal asymptote? You're going to have to do this. That's the only way to be concave down, always decreasing, and meet the requirements of those asymptotes. Let's look at the far right point. It's concave up, right of 1. It's always decreasing. It's going to have to look like this. And then in between, notice it's always decreasing, so it's going to start up here probably, and down here probably. It's going to be concave up, and then our single inflection point right here, and then it becomes concave down. And that's your graph, best we can do. Hope this helped. This was long. These are long. Good luck.
Made with Doodlecast Pro.